there are fractional atomic weights for certain elements. Now, these fractional atomic weights are due to the existence of isotopes. Let me give you one example. Supposing if you take chlorine, chlorine exists in the form of two isotopes. Chlorine 1735, which has got an isotopic abundance of 75%. And there is chlorine 1737 with an isotopic abundance. I mean, the abundance of this isotope is 25%. This isotope is 75% in nature. So these are the isotopic abundance. Abundance are the availability of a particular isotope in nature. So chlorine exists in two different forms. Check this out. One with the atomic weight 35 and the other one with the atomic weight 37. Then what is the proper atomic weight of chlorine that can be given? You can calculate it this way. 35 occurs to an extent of 75%. Then 37 occurs to an extent of 25% by, of course, 100. So now when this is simplified, you'll get 35.5. This is the atomic weight of chlorine, what we normally consider. You must have seen this in the periodic table that is supplied to you, right? So very important, fractional atomic weights are because of the existence of isotopes, right? So this is very important. Now coming to isobars. Isobars are, of course, the nuclides of different elements having different atomic numbers, but same mass number. Atomic numbers are different, but mass numbers are same. Let me give you an example. Let me give this argon 1840. Then there is a calcium 2040. Come on, let us check the number of protons, electrons, and neutrons. I think you're all very much familiar with this. Come on, the number of protons in this is 18. Even the number of electrons is also 18. And the number of neutrons is 40 minus 18, nothing but 22. On the other hand, the number of protons in calcium is 20. Even the electrons is 20. Now the number of neutrons is also 20. Right? Now, if you see the thing, the number of, atomic numbers, of course, are different. Mass numbers are same. The number of protons are different. Electrons is also different. Even the number of neutrons is also different. But because, see, the mass number is same, I can tell you that the number of I mean, the sum of protons and the neutrons is same. Nothing but mass number. Of course, protons are different, neutrons are different, but the sum of protons and neutrons is same. Nothing but the number of nucleons is same. I mean, the mass number is same, right? And see, because they have got different number of electrons, obviously their chemical properties are different because they have got different number of electrons in the valence shell. Coming to physical properties, even they are different. They'll of course be different because two different elements will have different physical properties, obviously. Even the radioactive properties will also be different. So this is all about isobars. You know, we can actually give it this way also. Iso means the same. Varies means the heavy, having same mass or same mass number. In a similar way, isotopes can be given as iso means the same, topos means the position. Okay, because they occupy the same position in the long form of periodic table. They were given this name by study. Because no, if you consider the example what we have taken yesterday, hydrogen of course has three isotopes. But the long form of periodic table has given just one place for hydrogen, right? It is not given three places. I mean, they occupy the same position. All the isotopes occupy the same position, right? Now, coming to isotones, these are the nuclides having, of course, the nuclides of different elements. Having the different atomic numbers, different mass numbers, but same number of neutrons. Very interesting. Number of neutrons will be same in the isotope. Let me give you an example. Say silicon 1430, phosphorus 1531, sulfur 1632. Come on, let us check the number of protons, electrons, and neutrons. Number of protons is 14. Electrons is also 14. Number of neutrons is 16. Number of protons in this case is 15. Electrons is also 15. Neutrons is 16. 16 here, 16 here, 16 here. And if you observe the things carefully, you got different atomic numbers, different mass numbers, different number of protons, different number of electrons, but the number of neutrons is same. Because they have got different number of electrons, of course, in the valence shell, their chemical properties will be different. They have got different masses. In fact, they are different elements. So they'll have different physical properties, even different radioactive properties. These are, of course, isotopes. Hope this is clear. Now going for an interesting thing. Isodiaphers. Isodiaphers are again the nuclides of different elements. When I say different elements, they'll obviously have different atomic numbers, different mass numbers, but same isotopic number. You know, isotopic number can be mathematically given as A minus 2Z. Now, when this A minus 2Z is simplified, we know that A is a P plus N, right? Minus 2 into, we can write this Z as a P. 1P, of course, gets cancelled. And finally, this comes out to be N minus P. Is that right? 1N and 1P, N minus P. Now, this I call it neutron excess. So, A minus 2Z or isotopic number is nothing but neutron excess. These two are same. Same isotopic number, or you can also say same neutron excess. Let me give you an example to make it much more clear. Come on. Fluorine 919, sodium 1123. Let us now check A minus 2Z rather than going for the number of protons, electrons, and neutrons. Anyway, they'll be different. Let us check these two things. For clarity's sake, this is isotopic number, and this is, of course, neutron excess. Come on, what is A here? 19 minus 2 into 9. So this can be given as 1. Check out A minus 2Z in this case. 23 minus 2 into 11. Nothing but 1. Then neutrons minus protons. What is the number of neutrons here? 10. Right. Minus number of protons is very clear. 9. So that comes out to be 1. Calculation, of course, is different. But overall, A minus 2Z is nothing but N minus P. Given it clearly. And how about the number of neutrons in this case? 23 minus 11 is 12. Minus the number of protons, 11. So that is equal to 1. Is that okay? So isodiaphers possess the same isotopic number or neutron excess. Of course, different number of different atomic number, different mass number, different number of protons. If you want, you can also check the number of protons, electrons, and neutrons. Come on, let us see them also. Protons, electrons, and neutrons. Number of protons is 9, number of electrons is 9, number of neutrons is 10. In this case, it is 11, 11, 12. Come on, let us check. Atomic numbers are different. Mass numbers are different. Number of protons is different. Electrons is also different. Neutrons is also different. Obviously, the chemical, physical, and the radioactive properties all are different, right? But only thing is they'll have the same isotopic number or same neutron excess. These are called isodiaphers. Now let us go for isosters. You know, isosters have same atomicity and the same number of electrons. What do you mean by atomicity? It is nothing but the total number of atoms in a molecule. Let us check, taking an example. Suppose you got CO2 and then N2O. Come on, let us check the atomicity of both. And even the number of electrons needs to be checked. If both are same, then only we call them isotopes. How many atoms are there in this? You can see 1 carbon and 2 oxygens, right? So the atomicity of this one is 3. The total number of atoms present in CO2 is 3. Even in case of this also, you got 2 nitrogens and 1 oxygen, right? So there are a total of 3 atoms, correct? Now coming to carbon dioxide, the number of electrons is carbon. You know that the number of electrons is nothing but its atomic number. Carbon, the atomic number of carbon is 6. 6 plus in oxygen, you'll have 8 electrons. 6 plus 2 into 8, isn't it? 6 plus 16, 22 electrons. Coming to nitrogen, you got 2 nitrogens. Each nitrogen contains 7 electrons. And then there is oxygen consisting of 8 electrons. So 14 plus 8, 22. Yes, they have got the same number of atoms and same number of electrons. So they are called isotopes, right? Now, let me tell you what isoelectronic species are, or what is isoelectronic series. Let me just give you that the isoelectronic, iso means the same, as I said. Now these are the species which consist of the same number of electrons, right? Species having the same number of electrons are isoelectronic. Let me just give you a very big example. Hope you all got my point. Coming to the number of electrons in all of them. Come on, check out. See, in this case, it is a 6 plus 4. In this case, it is a 7 plus 3 because minus refers to the thing that it has gained electrons. You all know that. 8 plus 2, 9 plus 1. It's a neutral one, neon, with no charge at all. In this case, it is 11 minus 1 because positive charge refers to the thing that it has lost electrons. Negative refers to the thing that it has gained electrons. Then this is 12 minus 2. This is 13 minus 3. And this, of course, is 14 minus 4. Right? All of them have got 10 electrons. The total number of electrons in all of them is 10. And you know, such a series is said to be isoelectronic series. All of them have got the same number of electrons. You know, in fact, we can also discuss about the sizes of these species. You know, as the magnitude of negative charge increases, size increases. And as the magnitude of positive charge increases, size decreases. Only in case of isoelectronic species. Let me tell you why. Coming to the order, it can be given this way. But why? Let me tell you two things in detail. Coming to this C-4, I mean carbide ion. The total number of electrons is 10, right? You got 10 electrons, but only 6 protons. Let me give that information clearly. Number of protons is 6, but the number of electrons is 10. Your nucleus has only 6 electrons, and those 6 electrons pulling the 10 electrons. I mean, the charge or the positive charge of the protons felt by each electron is not even 1. It is only 0.6, right? Every electron is feeling a positive charge of only 0.6. Let us check this one here. In this case, you got 14 protons, but because it has lost 4 electrons, it can be given as 10. 14 protons in the nucleus attracting only 10 electrons. So what is the charge? I mean the positive charge felt by each electron. It is more than 1. This is what I call effective positive charge or effective nuclear charge. Nucleus contains, of course, protons and neutrons. Protons are positively charged, neutrons are chargeless. In this case, the charge felt by each electron from the protons is, of course, least. Every electron is feeling, is, of course, experiencing a positive charge of only 0.6 units on it. So the attraction will be very less. Whereas when you come here, come on, every electron is experiencing a charge of 1.4 effectively. So effective nuclear charge, effective positive charge is more in this case. When you have more attraction, the nucleus attracts the electrons strongly towards itself. If more protons are there, of course, here you got the same number of electrons. If there are more protons to attract electrons, then of course they'll be attracted strongly. If you got less protons, like in case of carbide, of course the attraction power will be less. As a result, if attracted more, the size will be very, 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 very less. In this case, because they are attracted strongly, size decreases. I mean, this is in case of this. Whereas if you consider this, you got less protons in comparison, but you got the same number of electrons. Even here also you had a 10 electrons. In this case, of course, you can attract, I mean the nucleus can attract the electrons, but this attraction will be less effective. When the attraction is less effective, you cannot attract the electrons strongly. Less effective, whereas in this case it is more effective. More effectively pulled, least or smaller is the size. Size will be less. In this case, size will be more. I mean, it doesn't decrease that much, is what I would like to say. So that way, if effective nuclear charge is less, size will be more. And if effective nuclear charge is more, size will be less. If effective nuclear charge is more, nuclear attraction will be more, isn't it? So this is what you have to concentrate on seriously. In this case, nuclear attraction is less. That is the reason why when attraction is less, size of course doesn't decrease too much. Here attraction is more, so size decreased too much. So that is the reason why silicon +4 has got least size. So finally, what I would like to see, in case of isoelectronic series or isoelectronic species, as the magnitude of positive charge increases, what? Size decreases. And as the magnitude of negative charge increases, size increases. Got it? Positive charge is increased, +1, +2, +3, and finally +4. Size is least, size decreased. Negative charge is increased, size increased. Maximum size is for C-. Don't think that silicon is the biggest atom. No, when you are comparing an isoelectronic series, then this is what you have to concentrate on. Okay. So this is about the isoelectronic species. You know, there is something called nuclear isomers. What are nuclear isomers? Interesting. You know, these are the nuclides of the same element having same atomic number, same mass number, but differ in radioactive properties or radioactivity. Let me see. I can also tell you that they differ in the stability of the nucleus. I told you that radioactivity is because of the unstable atomic nucleus. Let me give you an example. Let me give you cobalt-60. Even the other also cobalt-60, but let me put a star mark over this. What does this star mark indicate? Both are cobalt-60 only. But you know, this star is what actually makes it different. The star refers to the thing that this cobalt has a metastable nucleus. What do you mean by metastable? Not so stable, medium stable, or less stable when compared to this. This one has, of course, a more stable nucleus. But why is this different? Why is one cobalt has a more stable nucleus? Why the other one has a metastable nucleus? See, sometimes during the formation of the nuclei itself, there happen some deformities, I can. Finally, it ends up with a nucleus which is unstable or less stable or medium stable. So that is how, though both are cobalt only, one has got a metastable nucleus, and the one that has metastable nucleus, you know, this exhibits radioactivity. right? So that is about nuclear isomers. All are same. I hope you know that the atomic number of cobalt is 27, right? 2760, 2760. But only thing is, one has a stable nucleus, the other one has a metastable nucleus. Now let me give you something which is much more interesting. See, when uranium 90 to 237 emits an alpha particle, I told you that when you got too much a difference in the number of protons and neutrons, the nucleus bulges. The nucleus becomes so large that it undergoes a spontaneous disintegration. I mean, disintegration or breaking on its own, during which alpha, beta, gamma rays are emitted. I told you that the alpha is nothing but, alpha rays consist of alpha particles, nothing but helium nuclei. Now you are subtracting the He24, 92 minus 2. How much is that? 90. You know, you get 90 and say this 237 minus 4. How much is that? 233. Is that okay? Now, when this thorium 90 233, I hope you know that the element with atomic number 90 is 90 is thorium. It's, of course, the one that belongs to F block, right? Actinium series, or it belongs to actinide. Now, when this emits a beta particle, I told you very clearly that beta is a fast moving electron. I told you this yesterday itself, but this electron, remember, it is not the one that is revolving around the nucleus. It is the one that has come from a neutron after disintegration. Remember, it is not an extranuclear electron. I told you this yesterday. Now, look at this, 90 minus half a minus. Nothing but 91. 233 minus a 0 is nothing but 233 only. So that is protactinium. Pa is protactinium. Now when protactinium again emits a beta particle, come on, emit. When it emits a beta particle, 91 minus of a minus 1. That comes out to be 92. 92, and when a beta particle is emitted, obviously, there won't be any change in mass number. Now, I just want to give you one very interesting thing. Let us check the first one and the last one. How about these two? They have got the same atomic number, but different mass numbers. I think I can call them isotopes, right? Let me write that. See, when a nuclide emits an alpha particle, what do we get? No, just a second. One alpha particle, of course, we have actually got one alpha and two beta, right? Let me write that. One alpha particle and two beta particles in succession. In continuation in succession, its isotope is formed. Am I right? One alpha and two beta particles are emitted in succession. Point number one. Come on, let us check one more. How about these two? That is when an alpha particle is emitted. Let us check the relation between uranium and thorium. The first two. You know, here let us check the A minus 2Z. What is A here? 237 minus a 2Z. 2 into 92. I mean 184. 237 minus 184 is, I think it's 53, right? Come here. 233 minus 2 into 90. 233 minus 180. Nothing but 53. So they have got the same isotopic number. What do we call them? We call them isodiaphers because they have got the same A minus 2Z. So let me write that point here. You know, when a nuclide emits an alpha particle, its isodiapher is formed. Right. Now let us check the relation between things formed when a beta particle is emitted. Come on, check this out. Hope you can see that they have got the same mass number, but different atomic numbers. What do we call them? They have got the same mass number, but different atomic numbers. Yes, of course, they are isobars. Even these two are also isobars. Check out. Having the same mass, of course, a beta particle is emitted. See, generally, when a beta particle is emitted, we get isobar. See, when a nuclide emits a beta particle, its isobar is formed. Of course, this all comes under nuclear chemistry, but still, I just wanted to give this information because we all are very much aware of what alpha particle is and what a beta particle, right? So check this out. Let me just give you some more information. You know, the radius of atom is of the order of 10 power minus 8 centimeters. I mean, this is nothing but something multiplied by 10 power minus 8 centimeters, or the same thing can be written as 10 power minus 10 meters, because 1 centimeter is equal to 10 power minus 2 meters. Now, radius of nucleus is of the order of 10 power minus 13 centimeters or 10 power minus 15 meters. So from this, you know, we can write it as radius of atom is about 10 power minus 8 by 10 power minus 13. That is equal to 10 power 5 times. Isn't it? Let us put this in brackets. That is for your information. is 10 power 5 times to that of nucleus. We are just comparing the radii. Radii is a plural form. Radius of atom is of the order of 10 power minus 8 centimeters, and that of nucleus is of the order of 10 power minus 13 centimeters. Remember this, 10 power minus 13 centimeter or 10 power minus 15 meters is called Fermi, because radius of nucleus, is expressed in terms of Fermi unit. Now let me also give you one more information. The radius of nucleus R can be given as directly proportional to cubed root of its mass number. A is mass number, R is radius of the nucleus. Right. Now let me write this as, removing the proportionality. I am writing a constant. Now this R naught as a proportionality constant. Whenever you remove a proportion, you have to write a constant. So this proportionality constant has, of course, a value equal to 1.4 Fermi. Of course, it ranges from 1.25 to 1.5 Fermi, but generally we consider it as 1.4, taking almost the average value of 1.25 and 1.5. So this is a very important relation using which you can calculate the radius of nucleus, provided you know the mass number. Of course, we know the mass numbers. Don't get confused with the two words mass number and atomic weight. Atomic weight adjusted to the nearest integer is mass number. They'll almost be the same. Atomic weight and the mass number. Okay, atomic weights are generally, they'll be in fractions also, but normally the mass numbers will never be in fraction. We have seen that. Like chlorine 1735. 35 is the mass number. It can even be 37. But finally, the atomic weight has come out to be 35.5. That is in fraction. So the atomic weight adjusted to the nearest integer is mass number. Don't get confused with these two words. Okay. That is about the radius of nucleus.